evening, or afternoon, everyone. Thank you for joining us live or on demand, especially as we head into the end of the year here. My name is Brandon Reeves, Product Marketing Manager here at EMQ, and I'll be moderating today's session. Today's webinar is titled From MQTT, Data to Time Series Insights, and it's a joint session between EMQ and GreptimeDB focused on a new capability we've introduced called EMQX Tables. For many teams, MQTT is already the backbone of their real-time data pipelines, and the challenge usually starts once that data needs to be persisted, queried, or turned into operational insights. And that often means exporting MQTT data into an external time series database where you manage connectors, schemas, retention policies, and additional infrastructure. So EMQX Tables was designed to simplify that workflow by bringing native time series storage and SQL style querying directly into EMQX Cloud, which is meant to reduce both architectural complexity and overall latency. Before we dive in, let me quickly introduce the speakers joining me today and how the session will flow. And a quick thank you to all of our speakers for joining us and for the time they've put into today's session. We'll start with Ben G, our VP of Products at EMQ, who will introduce EMQX Tables, walk through the product experience, and show how it works in practice within EMQX Cloud. Next, we have Ning Soon, CTO and co-founder of GreptimeDB. He will go deeper into the architecture behind EMQX Tables and compare this approach with traditional time series databases like an InfluxDB. Then we'll share a short pre-recorded customer segment with Henry Chen, software engineering manager over at TVU Networks, where he's going to walk through how their team is using EMQX Tables in a real production environment. And then we'll, of course, wrap up with a live Q&A at the end. Before we get started here, just a couple of quick housekeeping notes. This session is being recorded, and we'll share the replay and slides afterwards. Expect some time within the next week. Everyone will, of course, be muted during the presentation, but you do have free reign to leave comments as we go throughout the presentation here, so I please encourage you to do so. And we'll answer as many as we can during the final 15 minutes. And if we're unable to get to your questions live, we will be happy to follow up with you after the session, so don't worry. And with that, I'll go ahead and hand things over to Ben to kick us off with an introduction to EMQX Tables and a walkthrough of the product. Ben, over to you.
Thanks, Brandon. Hello, everyone, and thank you for joining us today. My name is Ben, and I'm the VP of Product here at EMQ. I'm very excited to share something we have been working on for a long time. And today, we're introducing EMQX Tables. This isn't just a new feature. It is a fully managed time series database built directly into EMQX Cloud. And it is a big step forward for us, and I think it will be a big help for you. So here's what we will cover today. And first, I want to explain why EMQX Cloud is evolving. We're moving from a single SaaS to a complete platform as a service. And then I will explain what EMQX Tables actually is and the problems it solves for IoT developers. And I will show you how it works, the flow from the broker to the table, and how you can visualize the data using SQL or Grafana. And after that, I will show you a live demo so you can see it in action. After my part, Ning, the CTO of GreptimeDB, will take you deeper into the architecture and performance. And later, Henry from TVU will share a real custom story and how they are using EMQX Broker and Tables in practice, and why they choose EMQX Broker and EMQX Tables. Let's start with a story I hear from our customers every day. And for a long time, EMQX Cloud has been the best place to connect your devices. But we realized something important. Connecting the device is only the beginning. The real work starts after the data begins to flow. Imagine you have thousands of devices connected. Data is pushing into the broker. And immediately, you have questions like, where do I store all this data? And how do I process it in real time? And how do I make use of it? So in the past, the answer of these questions You have to build a complex architecture. You had your broker here, a separate database there, and maybe a stream processing tool over there. And you had to write custom group code to stick it all together. And it was complex, it was expensive, and it was fragile. So we are building EMQX tables to fix this, and we are evolving from just a managed MQTT broker into a unified MQTT data platform. And the first step is integrated storage. So take a look at this image. Does this look familiar to anyone? So this is the integration maze. When you try to build your own IoT backend, you end up with data moving across too many systems. You have too many systems to manage, and you spend too much time on integration work instead of building your application. And most importantly, it slows down your time to value. And every time you want to add a new sensor or a new metric, you have to update the broker, update the ETL pipeline, and update the database as well. It's a headache. So we built EMQX tables to cut through that maze. Here is what makes it special. First, seamless integration. You don't need external connectors. You don't need complex code. The data flows directly from the MQTT topic into the database through our rule engine. And second, it is my favorite feature, the auto schema inference, or we call it schema on the fly. In traditional databases, you have to define the table schema before you send the data. If the device adds a new field, the database breaks. With EMQX tables, you just send an MQTT message the way you like. We analyze the message and we create the table and the schema automatically. And when the message changes, the schema in the database changes accordingly. Third, it is high performance. It is optimized for IoT workloads handling millions of data points per second. And you can query your data with SQL, the language everyone knows. But we also support PromQL if you are coming from the Prometheus world, and Influx database line protocol if you are migrating from Influx database. It's your choice. And you can connect tables directly to Grafana, Metbase, or Streamlit. No extra adapters, no custom plugins, and just point to your visualization tool at tables and start building dashboards. And finally, it is fully managed. We handle the scaling, the backups, and the infrastructure. You just focus on your data. So how does it actually work under the hood? It is a simple four-step process. Step one, create a connector. So your EMQX broker and EMQX tables live in the same cloud environment, and they talk to each other over the internal network. It's fast, secure, and no public internet involved. And step two is to define your rule SQL. In the rule engine, you write a simple SQL query, something like select star from a device topic, and this tells the broker which messages to capture. And next step is to configure an action, and you set up an action that writes the captured data into tables. And we use InfluxDB line protocol. It's efficient and well suited for time series data. And last step is to query and visualize. And that's it. Your data is now in tables, and you can query it immediately using our built-in SQL editor, or using MySQL or Postgres drivers if you want to fetch the data in your own applications. And or you can connect with Grafana and start building dashboards. And so from raw MQTT messages to actionable insights just in 4 steps. So once the data is stored, you need to see it. We provide a built-in SQL editor directly in our dashboard. And if you know standard SQL, you already know how to use EMQX tables. So there's no new language to learn. But we know many of you love Grafana and Prometheus, so we support PromQL as well. And you can add EMQX tables as a standard Prometheus data source in Grafana. And this means you can build beautiful charts and dashboards in minutes. By seeing is believing, let's jump into a quick demo and to see how we can configure this pipeline in just 1 or 2 minutes. So first, let's go to this EMQX console. And before the demo, I already have 2 instances set up. One is the EMQX broker, and another one is the EMQX tables. Both of those 2 deployments are running in one project. That means they are running in the same network. So the connections are using the internal network, not the public internet. So this saves you money on data transfer and makes the connections much more secure and efficient. So first, let's take a look at the EMQX tables instance. This is the overview page, and you can see the connection info here. And here you can see 2 endpoints. One is for public access. For example, if you have an external server service that needs to query data, you can use the public host. And by default, we also provide an internal endpoint. The EMQX broker will use this internal address to write data directly. And on this page, you can also see monitoring metrics like CPU memory, storage usage, and also the network traffic. So if you click the monitor page, you can see more metrics over a longer period. Now let's confirm this database is currently empty. So click the Data Explorer. So this is a built-in SQL tool for querying data. And on the left side, if I expand the database, you can see there's no tables here yet. So I can also run show tables, run query, and you can see no tables returned. So this is correct. And in a moment, you will see that when we send an MQTT message, the table will be created automatically. Now let's go to the EMQX broker instance to set up the integration. So for this demo, I'm using an EMQX dedicated flex deployment, while Serverless Works 2, the dedicated plan allows for these secure internal network integrations. So remember the 4 steps I mentioned earlier. So let's click the data integration. Okay, so step 1 is to create a connector, and I just need to find the EMQX tables and click Get Started. So because the broker and the tables are in the same project and in the same region, we have a shortcut. I don't need to copy and paste URLs or credentials. I just select my deployment from this drop-down menu. No username, password, no database names, no endpoints to enter, just select the deployment. And then click Test to verify the connection works. And click New. The first step is done. So we have created a connector. And step 2 is to create a new rule. And just click the new rule. So in this step, we can specify how our broker can catch the data from the topics and how we want to process the data before we send to the database. So here I prepared a SQL to get the data and filter the data. So if you know SQL, it's easy to understand. So we are listening to the topic called test. And when a message arrives, we extract 3 fields: and device ID, and temperature, and the humidity. I also used a built-in function to get the server timestamp as a false value, even if in the original message there's no timestamp in the MQTT message. So the rule engine is very powerful. It has many built-in functions for complex data processing. So that's it. Click Next. We finished the third step. So next step is to set up an action. So this tells the engine how to write the data. And I just need to enter the insert statement. We will use the InfluxDB line protocol here. looks like this. So here, environment metrics is the table name, and device ID is a tag, and temperature and humidity are fields, and finally the timestamp. So I click confirm. Okay, it's done. So simply 4 steps, and we have configured the integrations from the MQTT topic, data processing, and then insert into database. Now let's have a test. And before the test, let's go back to the tables to verify again there's no tables in the database. Good. Okay, so I'm using the MQTT. This is a client tool to simulate a device. And first, I need to connect to the broker and send a message. So in this message, it's a sample message. It contains 3 fields: device ID, temperature, and humidity. There's no timestamp in this message. And let me click send. All right, you can see we have successfully published a message, and we received the message through the client tool. And now let's refresh again on the dashboard. All right, so here you can see the new table is created automatically. The table name is environment metrics. And if you expand this table, you will see the fields here. We have a timestamp, we have a device ID as a tag, and then we have two fields. And we can run a query. Just use a select statement and click run query. And you can see now there's one row in this table, and this is the MQTT message we just sent to the broker, and the broker sent this message to the database. Now let's change another message. For example, let me change the device ID to 2 and also update the values. Click send again. Immediately click run query, and you can see the new message arrives into the database in a very short time. So that's it. It's very simple. You don't need to define the schema manually. The database adapts to your MQTT data automatically, and the data flow securely through the internal network without touching the public internet. It's secure, efficient, and cost-effective, and no glue code required. You just use our dashboard to configure the integration. Okay, now let's go back to our presentation. So now some of you might be wondering what's running under the hood. What database powers EMQX tables? The answer is GreptimeDB. And let me explain why we choose GreptimeDB. So IoT data has some unique characteristics. First, it grows incredibly fast. A decade ago, an IoT project might have thousands of devices generating gigabytes of data. And today, we're talking about hundreds of thousands of devices generating terabytes or even petabytes every day. And second, teams want unified observability. They don't want separate systems for metrics, logs, and traces. They want one place to analyze everything. And also, IoT data or IoT traffic is bursty. So devices don't send data at a constant rate. And you might have quiet periods and then sudden spikes. So your database needs to handle both without over-provisioning. So GreptimeDB was designed from the ground up for these challenges. It's object storage first. That means it stores data on S3 or GCS, not expensive local SSDs. And for long-time data, it can reduce your storage costs by 10 times or even more. And also, it's a multi-protocol compatible database, and you can ingest data using InfluxDB line protocol, and you can query using SQL or PromQL. This makes migration very easy. And it's also a cloud-native elastic, and compute and storage nodes can scale independently, and you only pay for what you use. And we believe this architecture is the future of IoT storage. And to explain this in more detail, we have a special guest today. And up next, we will hear from Ning, the CTO of GreptimeDB, and he will give us a deeper dive into the architecture and performance. I will hand it over to Ning now, and I will be back at the end for Q&A.
Okay, thank you, Ben. Thank you for having me on this EMQ session. Okay. Today we are going to explore the effective time series data storage for MQTT and how EMQX Tables as the new generation of cloud-native time series database can build a solid, scalable, and cost-effective foundation for your MQTT stack. We will walk through the architecture, performance benchmark, and some of the important features. So my name is Ning. I'm the CTO and the co-founder of GrepTime, where we build a specialized database for time series and observability data with the Rust programming language, open source technology, and cloud-based technology. You can find our company and my own work on our GitHub page. So we will start from MQTT itself. The EMQX Cloud platform has been a fantastic gateway for connecting IoT devices to the cloud. If we look at the typical payload of MQTT message, there are two categories. The first one is control message. Control message carries authentication, commands, configuration. It flows between your server and the device through the MQTT gateway. And another category is a data message. It's mostly about the telemetry data you collect from the device, the wearable or some electronic vehicle or something like that. It can be environment temperature, as we saw in previous demo. It can be a voltage of any electronic components, or location or speed of any GPS devices. Sometimes it also contains some performance data of the device itself. It's what we call observability data. You can collect this type of data to make sure your device is running normally, or use them as a baseline to optimize the performance, or just to address some code issues of a particular device. All these type of data are mostly time series data. So what makes time series data so special? Why we need a specialized database for time series data? First, time series data is mostly time indexed. It has at least one timestamp associated with the message, the values. In some cases, there are even more timestamps like generation time, collection time, and insertion time. So you will choose one timestamp as the index. So the data is organized, sorted according to this timestamp. Second, time series data is mostly write heavy. In most cases, devices can generate a lot of data at a fixed or not fixed interval. For example, in one of our customers' use case, they collect the signals from their electronic vehicle components that can generate the data at 1,000 hertz, which means 1,000 data points are generated per second. They need to use this raw data to analyze this behavior of electronic components in the vehicle for safety and the product of observability. Also, if you look at from a cloud perspective, as the number of your devices grows, the ingestion rate on the cloud database will get a multiplier very fast. Next, time series data is mostly immutable. So it means once the data is written, it never gets updated or deleted until it's expired. Cardinality is another unique concept of time series data. Each cardinality, or in other scenario we call it time series, represents a unique data stream of time indexed data. So in InfluxDB's data model, each time series is defined by a unique combination of all tag values. So most of the database follows this design, and so do us. Thus, the read pattern is completely different for time series data. So compared with traditional transactional data, users rarely do a single point lookup for time series data. They never give a timestamp to query one single line of value. So in most cases, it's a query for a given range of time. We use aggregation, analytical, and such type of queries to find the data trends. It's not based on one single particular data item. So this is the unique traits of time series data. So with all these times unique traits, let's look at how EMQX tables that's powered by GreptimeDB, how we address them. So here we are comparing EMQX tables with traditional general purpose relational database like MySQL, MongoDB, or traditional time series database like InfluxDB, especially for InfluxDB V2, and TimescareDB, which is modified or developed based on Postgres. So in this comparison, I think we are particularly strong at these three areas. The first, we can handle massive data ingestion rate and the massive data size. So with EMQX table or GreptimeDB, adding storage or computer resource to your cluster is very simple. There's no data movement required in this process. We use object storage as main storage, so you don't have to do data replication. You don't have to do backup for data for duration. Also, the object storage is very affordable compared to local SSD. In some stats, it costs only 10% compared to traditional local disk. Second, we have additional index mechanism to deal with high cardinality queries. At last, we use columnar data format, which is optimized for analytical query. So in columnar data format, data is physically organized together for a sequential scan. So you can get the stats, get the aggregation result very quick by just scan a range of data. The column storage also allows us to use some encoding method to reduce the data size that persistent on the main storage. We can use it as a compression method, so you can save a lot of space and storage cost based on this encoding compared to traditional general purpose compression. Okay, next we will take a look at the high-level architecture of GreptimeDB. So from the full picture, GreptimeDB is sitting as the base of your data stack. Application will connect to the database for data ingestion, the query. In GreptimeDB, we have a concept like database and the tables as in MySQL or Postgres. I think you are already familiar with this basic concept. And in GreptimeDB, tables are split into regions further for horizontal scaling. So regions is the minimal unit for handling data, for maintaining data. This is the concept level. So in GreptimeDB, there is three major components. We call them front-end, data node, and meta server. Front-end is responsible for talking with the application. It's a completely stateless item, component, which means you can add a front-end instance without any maintenance effort. It's responsible for handling protocols and returning data back. It has a table and the region information cached in every front-end instance. If it has an ingestion request incoming, it will convert them into a standard format, standard internal format, and split the ingestion request and route them to downstream nodes accordingly. As I said, we have several protocols supported, so we use a standard internal format for internal communication. And if the incoming request is a query, it will pass the query and generate the query plan. If the query involves multiple stages to execute, front end is responsible for sending them to downstream nodes and execute them, merge the final results together as a query response, and returning back to the application. So this is basically how the distributed query engine works at high level. Next, the data node is responsible for storing and serving table regions. As I said, the table regions is the minimal unit of how we maintaining data. Internally, we use LSMGs for our storage engine. So data is buffered in memory on ingestion, and for some time. So once it hits the threshold, or it hits the time threshold, it will be flushing to the object storage in batch. So data node also runs query against the table region data it serves. Front end is responsible for route those queries. We use Apache Arrow data format in memory and Apache Packet format for object storage. All these formats are open source standard format. It has very good interoperability with other open source tools. And to speed up the query, the data node also maintains caches and index for the query speed up. Yeah. At the bottom, this is the meta server. Meta server is the brain of the cluster. It hosts the metadata. It hosts the master metadata of tables and regions. It assigns those regions to data nodes and maintains heartbeat connection to monitor the cluster membership. So when you do scaling up and the scaling, new nodes may join the cluster, and when there is a failure, some nodes can be removed from the cluster. Metadata is responsible for monitoring all these changes. So once change is detected, it will reassign data regions to other data nodes to ensure the overall high availability of the cluster. And the meta server itself is a small subcluster in the whole components. It used leader election, and it used an external key value store to ensure the reliability for itself. So having all these components in GreptimeDB architecture doesn't mean it requires a steep learning curve of some very high starting resource requirements when you are starting using GreptimeDB. So we have a mode called standalone mode, as Ben demos. This standalone mode combines all these components into a single process. So this is perfect for getting started. And when your workload grows, you need more compute resource, you need more reliability. You can switch to cluster mode at any time. For cluster mode, this front-end data node and meta server are deployed as independent process, and each component can be scaled undefined. Next, we will check some performance benchmark. We will start with this TSBS benchmark. This TSBS time series benchmark suite is maintained by Timescale team. It's a very handy tool for testing time series databases. It has data generation and ingestion, and it includes some typical queries that can test the performance of time series database. The first one I want to cover is the TSBS comparison between GreptimeDB and InfluxDB versions 2 and their new release version 3. This is the ingestion rate comparison. You can say that we are about 1.5 times faster than InfluxDB3, and we are about almost 4 times faster than their early version. And for queries in TSDB, there are many queries they want to test every aspect of a particular time series database. So overall, if you compare the result, you can say that GreptimeDB is almost I think it's almost faster than InfluxDB3 in every benchmark, in every test. And for some tests that surprisingly that InfluxDB2 is a little bit faster, but you can say that we are quite close. Also, this test that InfluxDB2 is faster is almost mostly the simple tests. Most of the tests will finish in milliseconds, so we are not far behind. It's quite close. And once the data become complex or the query become complex, our query performance it becomes way better than this traditional database. And the next, this is the same test we made between TimescareDB, which is also I think you are familiar with for time series data, and GreptimeDB. For ingestion, we are almost I think it's twice throughput. Yeah. And for query, it's interesting that we are almost faster in I think in all the tests except the 2. It's last point and group by order limit. In only these 2 tests, TimescareDB is faster than us, and in our other complex queries, we are way more faster, I think. Yeah, by the way, to show all these chart all these results in a single chart, we use log scale y-axis. So even if this it looks quite close, but it's actually 5 times like this. Next, this is a JSON bench published by ClickHouse. Yeah, JSON bench is not a typical time series benchmark, but I'm going to include this because it's mostly about the data aggregation and analytical queries that you will do with your time series data. And then you can see that with 1 billion documents in the database for the code run. Code run means the first run. There's no cache available in this scenario. That GreptimeDB is the overall top database compared with ClickHouse and any other solutions. We are also quite impressive in data size. We are only 10% larger than ClickHouse, and I believe this still can be optimized. Yeah. Okay, next we will quickly go through some of the important features that can make your life easier with time series data. The first one has been already covered, that GreptimeDB supports a lot of protocols. The idea is to make the transition from other platform to GreptimeDB, make it easier. You don't have to learn a new concept. You don't have to use new tools, but you can benefit from our scalability and the cost effectiveness. So if you are on the EMQX platform, of course, we have a EMQX native connector available, and on the EMQX platform, you can also connect to the EMQ tables database directly with the endpoint available from the console, and you can use InfluxDB line protocol. And if you are from use some observability data stack, you might be familiar with OpenTelemetry. Yeah, you can use their standard SDKs and transport to ingest data into the database. We also have some SDK for our own custom optimized gRPC protocol. And for query, we are compatible with MySQL and PostgreSQL at the web protocol level. That means you can use their language drivers. For example, if you use Java, you can use their JDBC drivers to connect to the database directly with any. Yeah, if you choose MySQL, you can use MySQL. If you come from Postgres, you can use Postgres driver. The SQL is slightly different from vanilla MySQL or vanilla PostgreSQL, yes, because we have added some extension for time series. But in most cases, you can write SQL by your own, so the driver is just what you need. And if you are familiar with Prometheus, Prometheus is really handy for querying, for visualizing time series data. Their language is very easy to use, easy for visualization. And we have a full compatibility with all these protocols. Also, I want to mention that we built all this protocol compatibility from scratch in Rust. So we inherited some good points, but also we can avoid some bad parts. For example, in Postgres, they use the connection per process mode. So each connection is very expensive in vanilla Postgres. But in GreptimeDB, we are fully asynchronized architecture, so you can have a lot of connection connect to the database. It's okay. And by the way, we also have an MCP server. Nowadays we talk about AI everywhere. We have a GreptimeDB MCP servers that can talk to you can configure your agent to talk to a GreptimeDB in your AI application. It's very handy. Okay. So for query and the data model features, I think the most important feature is the auto schema, as Ben suggested. Yeah, with auto schema, you don't have to create a table. You don't have to run DDL ahead of time. So columns are automatically added when data comes in. Next, for query, we support most Postgres datetime functions. Postgres has a very good foundation of use of these functions. We almost compatible with all these datetime functions. And we also have our own extension to standard query. This is called range query. This is because writing time windowed aggregation in raw SQL is not an easy task. So we add some extension, add some clause for you to make this easier. Next, materialized view. In GreptimeDB, we call it flow. This is a feature that allows you to run aggregation as data comes in. It's very helpful when you have some fixed but very expensive analytical queries defined in the database or in your BI tools. This feature will pre-compute and persistent result data in materialized views. It's just another table. So in your next query, when you want to visualize it, it's just fetch the data from the database without repeated computation. So trigger rules. Trigger rules is very similar to Flow. It's an in-database compute engine. it will continuously evaluate your data against some predefined rules. In this example, this predefined rules is defined in SQL query. So anytime when this SQL query returns some results, it will trigger, it will be treated as the rule is matched. It will trigger the webhook you defined here. Yeah, you can use this mechanism to send some notification when there's anomaly data detected. You can send notification to your PagerDuty or to your Slack channel. It's okay. So trigger rules. This feature will soon available in EMQ tables. It's a new features that we plan to have in the coming release. Okay, to summarize all this important information, I want to share with you that the first having EMQX tables or GreptimeDB is running on Kubernetes and object storage. So this database is as scalable as your application. You can add computer resource and the storage resource at any time without much operation effort. Second, we use efficient compression and cost-effective data storage. We use object storage to make life easier without paying much about storage or operation cost. You can keep historical data as much as possible. You don't have to expire data due to storage cost. The third, we use columnar data format and the open source query engine. This is powered by Apache Arrow ecosystem, Arrow Packet, Data Fusion, yeah, all these open source tools and standard tools. We are high performance for ingestion and query. We have multiple protocols supported. We have in-database compute engine for materialized views and trigger rules. Okay, yeah, this is all I want to share for today. So next, I recommend you to start your own EMQX table trail, and also you can learn more about GreptimeDB from our document site. We will share these slides with you later.
Thank you, Ning. Continuing on here, as I mentioned at the start of the session, Henry wasn't able to join us live today, but he was kind enough to record his segment in advance, so we could still share TVU Networks' experience with EMQX tables so far. So with that, let me go ahead and start the recording.
Hi everyone, I'm Henry Chen, Software Engineering Manager at TVU Networks. At TVU, my team builds the media workflow that uses MQTT to publish real-time matrices and use deliver control commands to media modules across our production systems. Today, I'm excited to share how we use EMQX Broker and tables in a real production environment. Before we get started, here is a quick overview of today's agenda. I will begin with a brief introduction to TVU. Then I will explain how we use EMQX Broker and tables to build our media matrix and control pipeline. Next, I will talk about why we select EMQX from both a technical and a cost perspective. And finally, I will share some earlier benefits and improvements. About TVU Networks. TVU Networks stands as a leading global provider of SaaS and cloud-based workflow solutions spanning diverse industries. Leveraging AI, microservices, and automation-driven technology, TVU facilitates streamlined metadata and story-centric workflow in live video acquisition, production, and distribution. I will introduce how TVU is using EMQX broker and tables. At a high level, our workflow consists of three main parts. First, media module publish a real-time matrix via MQTT. This allows us to collect the matrix in a lightweight and scalable way. Second, these matrices are ingested into EMQX tables using the rule engine and the connectors, made available for querying and visualization. And third, we use MQTT to send the control commands to the media modules, which allow us to control the settings without opening any inbound network ports. Why did we choose EMQX? Here are 6 key reasons. The first, cost efficiency. In cloud deployments, the cost of 1,000 connections and 1,000 TPS is reduced by over 80% compared to AWS IoT solutions. Second, the full MQTT protocol capabilities. EMQX full support the MQTT standard. That means we could use any compliant open source MQTT client without vendor lock-in. Third, the freedom to run performance testing. We can run unlimited performance and stress tests without the risk of unaccepted cloud billing. Fourth, the rich data pipeline options. EMQ connectors enable seamless data integration with minimal custom code, simplifying our matrix and data pipelines. Fifth, strong on-premise deployment support. Some customers require internal or isolated network deployments, and EMQX provides flexible options across cloud on-premise environments. Six, flexibility of EMQ tables. EMQ tables support SQL, PromQL, and LAMP protocol, make it easy to integrate with existing monitoring and analytics workflows. About the published matrix workflow. So we have many media modules processes. These processes send matrix information to broker, and broker send it to rule engine. The rule engine will distinguish which type of these media modules and rewrite to the LAMP protocol and then send it to the tables. And depends on the different types of the media modules stored in the different tables. It's pretty efficiency, and our TVU dashboard use SQL or PromQL to querying from tables. About control pipeline workflow. So TVU control GUI will send the message to our TVU control service first. Like I want to change the bitrate. Then control service will forward this command to broker, and broker forward this command to media modules. So each media module process will subscribe different topics. If we use WebSocket instead of broker, that means our control service need to have a recorder, like this module use this connection. You could say the broker makes things more simpler. If we have many media module processes running, that means we should have a few control services to manage all the WebSocket connections. If media module process A connected to the TVU control service A, but the control GUI sends the command to the control service B, that means control service need to handle this situation, like how to forward this command to control service A, and then forward the message to process A. So if we use broker, the EMQX broker will handle all these connections. That will make the control service logic pretty simple. About earlier benefits and improvements, extremely easy to use due to MQTT components. Conformance might without having turning. EMQX offload infrastructure complexity. And our team focuses more on functionality than infrastructure. Okay, overall, EMQX help us simplify our media matrix and control workflow a lot. Okay, that's all. Thank you.
All right, thanks again to Henry for putting that together. If you have any questions specifically related to TVU Networks experience, or you would like to learn more about how they're using EMQX tables in production, please do feel free to drop those in the Q&A. And while Henry isn't live with us today, we will be happy to relay those questions back to him after the session and follow up. And with that, let's just move into the QA. If you haven't already, feel free to submit your questions using the panel at the bottom. We've tried our best to answer some live through text, but in the meantime, let's go through there. 1 second as I comb through these. Starting at the top here, thank you, Jing. Can I access the data from my own backend application or only from inside EMQX Cloud?
Yeah, I can take the question. So yes, you can access it from anywhere. As I demoed, we provide the public endpoint as well as the private endpoint. So while the broker uses the internal network for speed and security, and we also you can also use the public endpoint so that you can write the data into the database directly through your applications. And also you can use the third-party analytical tools using the HTTP or SQL clients. And also if your application is running in the same region as the tables instance, and we also support connecting EMQX tables through the private link. And we can help you to configure the VPC pairing or private link.
Great, thank you, Ben. Another was, this is from Aaron. What's the trade-off for using object storage as a main storage?
Oh, I think I can answer this question. Object storage has some benefit and also has its own drawback. And the major drawback compared to local disk is the latency. Yeah, we use HTTP to talk to S3, so the latency is much significant compared to local disk. So in EMQX tables, in GreptimeDB, we have several layers of cache to take care of this. We have write-through cache, so once your data is flushed to object storage, we also keep a copy as data in local disk. And we have a read cache when you are querying some data, for example, historical data from object storage. These data files are also cached in local disk for recent query. Yeah, I think this is the trade-off, but we do it. We have some special mechanism to deal with it.
Great, thank you, Ning, and thank you for the question. Another one here from Steve. Is EMQX Tables a separate product or part of EMQX Cloud?
Yeah, I can take this question. So EMQX Tables is a service inside EMQX Cloud, and you provision it from the same Cloud Console, and it integrates tightly with the EMQX broker through the built-in integrations and network options. So it's designed to feel like one platform, not two separate products.
Great, thank you, Ben. Another question here from Jing. I'm already using InfluxDB. How can I migrate to EMQX tables?
Well, Yeah, I can take this question. So that's a great one, and it is actually very easy. EMQX Tables supports the InfluxDB line protocol. This means if your devices are already sending data in that format, you don't need to change your device code. You just point the data to EMQX Tables via the rule engine. And also because we support standard SQL, your query logic might become even simpler.
Great, thank you, Ben. And another one here, this one's from Lauren. What data model would you recommend? I believe this is for you, Ben.
You mean the data model stored in the EMQX tables?
Yeah, which would you recommend, and how do you handle the schema changes?
Yeah, okay. So for IoT, we usually recommend a time series friendly model, like a timestamp, a device identifier, and a set of metrics. EMQ tables supports auto schema inference, so it can reduce the manual work when new fields appear. And that said, for production, we still recommend you keep your payload structure consistent and version your fields when you make major changes. And we also recommend using our Smart Data Hub feature in our EMQX broker, and it provides schema registry and schema validations, which can make sure your data is valid before sending it to database.
Great, thank you. Question from John here. Are there any plans to bring EMQX tables to on-prem installations?
Okay, a great question. So for now, EMQX tables is only available on AWS, and we will soon provide EMQX tables on Azure as well. And for the on-prem deployment, please contact our sales team, and we do have the options for enterprise customers. We can work with GreptimeDB team to help you set up EMQX broker and EMQX tables in your environment, no matter it's on-prem or it's on your private cloud.
Great, thank you, Ben. I know we're out of time here, but just a quick note to everyone asking about presentations and recordings. We will share both after this session. You can expect it within the next week or so. So you will have it in hand to play it back, and you'll also have that recording from Henry with the audio. So everything will be buttoned up and sent there. And with that, just want to thank everyone for the great questions and for spending time with us today. If you'd like to learn more about EMQX tables or anything else that we've covered here, everything on our site is well documented, as well as on GrepTime on DB's side. So do recommend that you check out, visit our website, look at our blog resources, our documentation, and many more. And we really just thank you again, and thank you to our speakers, Ben and Ning. Really appreciate you being here and joining us. And we hope everyone has a great rest of the year, and really wish happy holidays and a happy new year to everybody.
Thank you, Brandon.
Thank you, everybody.
Thank you,
Thanks
Brandon.
again.